Xiaoguo. I'm a postdoctor in Hangzhou Institute for Advanced Study, UCAS. Today I will share this report, probing the nature of dark matter while gravitational waves lensed by a small dark matter halos. And this paper is collaborates with Professor Eugene Lu. Okay. I will introduce dark matter and gravitational lensing. Then I will introduce how to detect the dark matter with the lensed gravitational waves from its lensed waveforms and lensing rate. Two aspects to introduce this. Then I will summary and results. So, the lambda CDM model is a standard cosmological model, and it has obtained the Nobel Prize, but there exist some problems in this standard cosmological model. For example, what's the nature of the dark matter and dark energy? According to the motion speed of dark matter particle, it can be divided into hot dark matter, warm dark matter, and cold dark matter. The hot dark matter particle is a very light particle, and its motion speed can reach light speed. Because its light speed is so fast, so you can smooth the large small scale structure. So for hot dark matter, the large scale structure will form at first. Then they will break into a small scale structure. This is the simulation tells us. And for cold dark matter, the mass of particle is very heavy, so it can form a small scale structure at first. Then this small scale structure will merge into a more larger scale structure. So is bottom up, and the simulation tells us. Sorry, the observation tells us in our universe, a small scale structure form at first, and they will merge into a large scale structure. So small galaxies will merge into larger galaxies. So we can exclude the whole dark matter because it's for large scale structure at first. So the ideal dark matter model could be warm dark matter or cold dark matter. And in the cold dark matter, the weakly interacting massive particles is an ideal popular cold dark matter candidate. But up to now, many dark matter particle detection experiments has excluded most of its parameter space. It will the detection limit detection sensitivity limit will be very close to the neutrino background, which means it could be impossible to detect such wind pool particle if we still we yet detect anything in the future. And someone used this poem to describe this situation. And even for cold matter, there also exist some challenges. This challenges called small scale crisis, including missing satellite problems, cosmic core problems, and so on. Missing satellite problems is say the simulation predicts like Milky Way, it should have a large number of dwarf galaxies or satellite galaxies, but we have not observed so many satellite galaxies for Milky Way. So this is a problem, and similarly, simulation tells us the density profile of diameter should be a cusp in the center, but some observation shows there is a cone in the center of diameter halo, and many other problems. So how to solve these problems? Some people think this should be observational effects, and because these galaxies will be influenced by baryon, so it also could be a baryonic effect. And there are also for example someone think the nature of diameter may be not full diameter but worn diameter or separating diameter or fuzzy diameter. For example, this is the density profile of separating diameter, and there is a core in the center of separating diameter. Okay, so maybe the core diameter is not the right answer. So and there exist many kinds of diameter models besides the WIMP diameter, include the worn diameter, separating diameter, and axion-like particles. This is a kind of fuzzy parameter. Could be. And it also can be the extra dimension and so on. And different diameter particles can have very different mass and cross section. They can cross very wide mass range and cross section over tons of order of magnitude, from the lightest fuzzy diameter to massive primordial black hole. The nature of dark matter is very important question. And how to detect the dark matter? Now we can use the gravitational lensing to detect the dark matter. So I will introduce. Three. Wait a moment. Okay. We can see the light from the background galaxies will be deflected by the foreground galaxies. So and sometimes we can see the multiple image of the background galaxies. This is the gravitational lensing phenomenon. So as predicted by Einstein, the light pass by a massive object like sun or other celestial objects. They will be deflected by the gravitation of this massive object. So this phenomena is gravitational lensing, and this is also an important test of Einstein's general relativity. And besides the light or electromagnetic wave, the gravitational wave will also be deflected by the massive objects. This is the gravitational lensing of gravitational wave. Yeah, but we have detected the gravitational lensing for electromagnetic wave, but we have not yet detected the gravitational lensing of gravitational wave. With the first gravitational wave, the detection of first gravitational wave events. So we begin to consider the length of lengthening of gravitational wave. For gravitational lensing, there exist two kinds of cases. If the lens is a very massive object like galaxies or galaxy clusters, the time delay between different images could be very long. Could be very long. So we can see multiple images of gravitational wave. But if the less less mass is small, the time delay between multiple images is short. We can see the distorted gravitational wave like this. Okay, and we can make a comparison between the lensing of electromagnetic wave and gravitational wave. The electromagnetic wave its wavelength is usually short, is much less than the scale of celestial objects. Usually is enough to use the geometry, the optics to describe the lensing of electromagnetic wave. But the gravitational wave is for the range we can detect, its wavelength is usually long, so it's easy to diffract. For this is if the length mass is less than this mass range for mini-hertz gravitational wave, so it will take place diffraction. And there are also many other differences. I would not comparison in detail. So then I will introduce how to detect the diameter with length gravitational wave. Firstly, we choose such kind of small diameter halo or minimal mini halos as our length. Its mass range is from 10 to 3 to 10 to 6 solar mass. Why we choose this mass range? Because in this mass range there will be less star formation, so there will be less baryonic effect. So we think it can serve as a plain proof of diameter without the influence of baryonic effects. And in this range, there will be the diffractive region for high frequency gravitational wave that can be detected by as LIGO, Virgo, and carbon. Okay. But we also need to strengthen in this for this mass range diameter halo. They are short of electromagnetic emission because there is no barrier in this diameter halo. So they are difficult to be observed by electromagnetic observation because they are short of such emission. And their electromagnetic wavelength lensing effect is also very weak because and it is difficult to be detected. Because its lens mass is small, so the angle between multiple images is too small to be resolved by our current telescope. And because these halos are usually far away from us, and they will not have significant motion in observation time. So it's unlike the stars. So there will be exist no significant variation of brightness. We can just see its little curve to detect such lensing effect. So we think the lensing of gravitational wave will be a unique tool to detect such diameter mini halos. Also, many papers have discussed using the gravitational lensing of gravitational wave to detect the diameter, but they many consider focus on the primordial black hole as the diameter model. but the primordial black hole, uh, the parameter space of primordial black hole has been constrained by many observations. We can see in a very wide mass range, uh, the fraction of primordial black hole in all diameters will be less than 10% in this very wide mass range. So is the primordial black hole is also not a very hopeful diameter candidate. So we need to consider more realistic density profile of diameter. The simulation tells us the density profile of core diameter could be NFW density profile. And the seven, if the separating diameter, it can have isothermal core in the center. What we call its density profile is isothermal core FW. So we consider actually several kinds of density profile for diameter halos. This is the scheduled Jeffrey density profile. It has three parts. In the center is the core. So the loop is black. And we its inner slope is -2, and the outer slope is -4. So it's more steeper than the NFW density profile. For NFW density profile, its inner slope is -1, and the outer slope is -3. As shown in this figure, the red line is NFW density. And for self-enlarging diameter, we assume it's at the isothermal core density profile plus unrefracted density profile, or the outside the isothermal core. The density profile of isothermal core can be solved from this equation. Because we don't consider the baryonic effects in this case, so the rho B is 0. Okay, now we can see the results in this figure. The green line represents the density profile for isothermal core, and the blue line represents the density profile for self-enlarging diameter. Combine the core diameter and isothermal core. And we consider two core size. If the core size is 0.1 times the scale radius, and or is 1. And another kind of density diameter model is the fuzzy diameter model. Fuzzy diameter model we is ultralight boson. Its mass could be 10 to minus 22 eV. Yeah. Because its mass is so small, so its deploy wavelength can be very large. it can reach the classic scale. So it will form a solid core in the center of fuzzy diameter model. The density profile of fuzzy diameter can be described by a solid core plus the minus 3 outer slope, like the NFW density profile. Outside the solid core. And the solid core density profile can be described by this formula. We can see in uh, in the transition region, the slope can be very steep. It can reach -16. And by the way, I want to strengthen. Although the mass of fuzzy diameter is very light, is a kind of cold diameter. Okay, then I will calculate according to their density profile for different kinds of diameter models. We can calculate the length waveform. Length waveform. We use amplification factor as F to describe the length waveform. It can be defined as the length waveform over the unlength waveform in frequency domain. And it can be calculated according to this formula. And we show the results for Sadio Jeffrey density profile here. This is the dimensionless frequency, and this represents the absolute value of the amplification factor. We can see its value represents the image. For example, is 4 represents the image will be amplified by 4 times. And we use the solar light to represent the results in wave optics. The dotted line represent the results in under geometric optic approximation. So we can see when the frequency is high, the results under the geometric optic approximation will be more closer to the results in wave optics. And we also show the results for 2 kinds of different models. One, the paper lights represent the results if the Sadio Jeffrey diameter density profile have a cone in the center. Its core size is 0.1. And the green line represents the results if the diameter density profile without a cone. So we can see the results without a cone will have more significant lensing effect is oscillating with frequency with higher amplitude. So its lensing effect is more significant if there without a core in the center. And this represents the phase of amplification factor in the lower panel. Okay, and then I'll also show the last waveform for different kinds of models. And the last waveform and the unlast waveform. The solid line represents the unlast waveform. We use normalize the frequency and normalize the amplitude. So we can see if we just change the black hole mass, it will not have a significant difference among different models. So their waveform is very similar to each other. And for the last waveform, we use different colors to represent different models with a core and without a core. They are also have different last waveform, and we can distinguish it from the unlast waveform. Okay, and then we also calculate the amplification factor for NFW, light density profile. We use different types of light to represent the different kinds of diameter models. With for tall diameter, we use NFW density profile, and for safe interacting diameter, we use isothermal NFW density profile. And the dotted line represents the results for NFW density profile. And we also consider the isothermal. The safe interacting diameter has two different kinds of different core size. With S is 0.1 and S is 1. I use dotted dashed line to represent the solid line to represent it. So we can see for NFW like density profile, its lensing effect could be much weaker than the DJF. Yeah, for such kind of diameter mini halo. But we they are still different from each other. So we can use distinguish different kinds of dark matter density profile from its last waveform or amplification factor. Okay. After that, then we can consider the difference between among them. Their lensing rate. How to calculate the lensing rate? I have is according to this formula. The lensing optical depth can be described by this formula. It's like a scattering problem. There exist many lengths between the observer and source. So its density number density is n. The number density times the cross section, okay, and integrate on the path from the source to observer. So we can obtain finally the lensing optical depth. According to lensing optical depth, we can calculate the lensing lensing probability, and then use the lensing probability times by the differential unlensed event rate. We can obtain the differential lensed event rate. Firstly, we will introduce the density, number density for different kinds of diameter model. We can see the red line represent the Hello mass function of cold diameter, and the green line and blue line represent the Hello mass function for one diameter with different particle mass. We can see in the small diameter Hello mass range, there will be much less 1 diameter in this mass range. This represents the number density in mass range. So the number density of 1 diameter could be much smaller than cold diameter in this mass range. And for fatty diameter in this range, 10 to 3 to 6 solar mass, the number density is too low to be detected. So we will not consider. We don't consider this mass range for fatty diameter because the event rate is basically 0. So if we consider fatty diameter, we need to consider the more massive mass range. We can also make a comparison among the different diameter models. The cold diameter its density profile is NFW density profile. For one diameter, we also consider, we also think its density profile is NFW density profile. For self-inacting diameter, we think its density profile is isothermal cold plus NFW. And for fuzzy diameter, is a Soliton cold plus NFW. The center of cold diameter is cusp. Is a cusp. For one diameter, although some papers say there could be a 4 or very small hole in the center, but the small hole can be ignored. So we also think it's the cusp. And the center of self-inacting diameter is the core, and the body diameter center is also and for the Hello mass function, the cold diameter Hello mass function is a power law. That is this red line. Basically a power law. But for one diameter, there exists much less small diameter halos in this mass range. For self-inacting dark matter we think is hollow mass function is the same as the cold dark matter. For fuzzy dark matter, cell will be is basically cut off at a small mass. Okay, and then we consider the the source. Yeah. The source we mainly focus on the binary black hole mergers as a source of gravitational wave source. We use this model in this paper. This merger rate is like this, and we can calculate its its this is the unlengthed event rate, and this is the lengthed event rate. We just use it as the lengthening probability. And this is for the high frequency band. For middle frequency band, we can definitely use this formula. And then I show the lengthening results. Lengthening results. We can see for Jeffrey model, the lengthening rate could be very high, and is lengthening effect is very significant. There will be much lot of lengthening events in this for this model. But if we consider more realistic density profile, NFW density profile, the lengthening rate could be much lower than Jeffrey. But for the DCGO and BBO, they still can detect significant lengthening events per year. And there exist two rows in this figure. The first rows represent the they have different threshold. The data row is 1, and this is for data row is 3. So if we choose a higher threshold, the lengthening rate will be lower. And for one diameter, we can see if the mass particle, the particle mass is much is smaller, so the lengthening rate could be also lower. But if the particle mass of one diameter is greater than 10 keV or 30 keV, the lengthening rate could be much significant. So it's possible to constrain the nature of diameter by this physical and BBO middle frequency gravitational wave detector. And for safety net in diameter, we also consider two cosines. They will have different results. If the core size is larger, the lengthening rate also be smaller. And this is different. This is Halo mass function and differential lensing rate for different bands. And we also consider the lensing rate for the fuzzy diameter halo. Fuzzy diameter halo. The lensing rate if we in this mass range 10 to 6 to 10 to 9 mass range is very low. Except the mass of the axion like particle is about 10 to minus 20 eV. Yeah. So in this case, there will be a lot of event rate. And we also show the differential mass distribution for different kinds of axion mass. So we can see we can use this to constrain the mass of axion like particle. And we also calculate time delay distribution and resolution angle. Use different colors to represent the different angles between different images. We can see it can for 3 images in strong lensing. Okay, and then I will discuss our results. We have not considered the binary dwarf merger rate at a high redshift. We use the merger rate will be much lower at high redshift. But if we consider population 3, the first stars formation or primordial black hole, this will be there will be more merger rate at a high redshift. It could be enhance. It could enhance the event rate, so it can enhance the lensing rate. And the density profiles of diameter mini halos is unknown. Yeah, we don't know what the realistic density profile could be. With only the simulation tells us it could be NW and that's all. But we don't know what the realistic density profile. And the halo mass function of diameter also is it can is also uncertain. Yeah, and the cone size also if there exists a cone in the center of diameter, it will also influence the lens range as lens rate. Then I summary my report. Combining the lens waveforms and lensing rate, we can prove or constrain the density profile and the halo mass function of the diameter. So we can constrain the nature of diameter. And assuming assuming the co-diameter, word diameter, if its particle mass is greater than 30 kV or 10 kV or self-infinity diameter model. The nature of co-diameter can be strongly constrained by middle frequency uh, space-based GW detectors, DCGO and BPO, use the length binary platform mergers by the or in spiral by mini halos of diameter. And we also found the lensing rate of self-inacting diameter depends on the size of its core. And if the diameter halo density profile is subdued Jeffrey density profile, the expected lensing rate could be very optimistic. And we also demonstrate the lensing rate and statistical properties of particles. Thank you. 啊，喂，都嗯啊，那个呃，这好，我直接用中文回答哈。就我看，因为它是中文讲的，然后首先就是希格斯场它不仅是跟暗物质有关嘛，就是它跟所有的，当然也不是说所有的，就是基本上，像重子物质的质量都是由希格斯场赋予的。然后它跟普通物质的相互作用，它应该不是这个四种相互作用里头的，它叫那个就是 Yukawa 和叫，当然我说错了，大家不要怪我哈。有些因为也就是也没有就好久没有接触这些东西啊，可能就忘了。然后希格斯场是不是暗物质？哎，其实就是有一种模型是，想想是，当然它跟那个希格斯场可能还不是同一个东西啊，就是有一种，就是当然它这个可能不是，因为这个就是涉及的理论模型太多了，可以说，然后而且就是如果不是去专门做这个每个方面，也可能不是很了解。当然我做的这个偏天文一些，然后他们这个做暗物质的也有，就是比如偏粒子物理的那种，嗯，但是我们是通过天文的手段去区分它，所以这个粒子物理的那个方面的可能不是很了解哈。然后我不知道，就是因为也没有得到回复，就不知道回答满意吗？就是首先它这个就是没法直接说吧，我觉得就因为暗物质就是你根据它模型不一样，就是不同的模型它可能跟希格斯场的关系都不太一样。比如说如果是圆柱黑洞的话，你说它跟希格斯场有什么关系，这个不太好说。然后比如说如果是一般粒子的话，它可能会有这个会是它的质量，就普通物质的质量，它可能是由希格斯场赋予。然后还有就是，对，就刚刚说的，就是希格斯场与普通物质的相互作用，它不是四种相互作，就是四种相互作用中的一种啊，它是那个卡瓦和康砖，当然就是也不是所有的粒子质量都是希格斯场赋予的，比如说像这里那个中微子的质量，它可能就是因为跷跷板机制产生的。 然后希格斯场是不是暗物质，还是就是像这里说的，就是说，也许哈，不知道，对，可能是一种模型哈。嗯，还有其他问题吗？嗯，对，说到这个，这里，嗯，你说可以可以，我都行。就如果没有什么问题就结束。嗯，行。